Okay, this video is for AP Calculus, and we're talking about approximating a solution curve for a differential equation using something called Euler's method. Let's go ahead and learn this procedure. Okay, we can't actually always find a solution to a differential equation analytically. We're learning these two methods to solve differential equations here in this course, and next year you'll learn another 15 or so methods to solve different forms of differential equations. But even after an introduction to differential equations course, an entire semester, there are still some differential equations that we can't solve by hand. There's just no way to get a written out solution curve. And when that's true, we still may need information to use the differential equation if we're using it to model something in the real world. So even if we can come up with an approximation of the solution curve, that can still be helpful. And so we use what are called numerical methods to find an approximate solution curve point by point, like essentially sketch the solution curve point by point. All we have to have is some way to have the first derivative, and we have to know the initial condition. And so the most famous method that is used is something called Euler's method. This guy produced a lot of mathematics. That is pronounced Euler. And we're going to learn his method. So this method requires that we have, this only works for the first order differential equation, which means you have to have only first derivative, no second derivative. But the right-hand side can be a function of either the x variable or the y variable, and you have to have an initial condition. So here's the idea. The idea is if we did have this differential equation, we could produce a slope field. What that means is if you plug in the initial xy point, you can find the slope of the tangent line right at that location. And then what you can do is you can go a little distance away, h in x. So we'll go a distance h away in x to get a new point, x1. And then we can say, well, whatever this change in x is, if I just take the slope and multiply by that change in x, that will give me the corresponding change in y. So I can take this y and add this change in y to that to get another y. So if I go like h over, if I take this initial x and I add the change in x, and I take this y and I use the slope times that change in x to find the change in y, I can get another point, which is, if it's not on the solution curve, it's going to be very close to the solution curve. It'll actually be on the tangent line, but the tangent line is approximate for the solution curve as long as we don't go too far away in this delta x. And then once you get that point, you use that point as a new starting point and go delta x again, add that, and then you multiply by the slope to get the corresponding delta y, and you add that delta y onto this second y to get the third y. And you keep doing that, and that traces out the solution curve point by point. So the formula that makes that happen is that the next y value is computed by taking the current y value that you're on and adding the change in y, which is just your chosen change in x, but times the tangent line slope evaluated at the current point that you're at. That delta y gets added onto this current y. And that's it. You just keep going until you get to wherever you want to go. So let's say that you have, like, this point starts at 1, 4, and you want to know this is 2, something. You would keep doing this until x became a 2, and then you'd have an approximation for what the y value is on the solution curve at that point. Okay, easiest to see by taking some examples. I have 2 examples here. You can maybe watch me do the first one, and then on the second one you can try pausing and doing it yourself. Okay, so this problem says use Euler's method to obtain a 4-decimal approximation for y of 1.5 on the solution curve for the differential equation y prime equals 0.2 x times y with the initial condition y1 equals 1. Okay, and now this one says, we're going to go from y equals 1 to y equals 1.5. And to try to stay pretty close, we're going to only go up a tenth at a time. So the delta x is only going to be a tenth. So we're going to go from x equals 1 to x equals 1.1 to 1.2 to 1.3 to 1.4. It'll take us 5 steps to get to 1.5. right, so the way this procedure starts is we start with the xy pair at the initial condition, which is x is 1, y is 1. I'm going to put that as an ordered pair of 1, 1. Sorry. And I like to make this in the form of a table. I guess not all teachers do this, but many do. So we're going to have our points on the curve on the left here, and then we're going to use the space to the right to compute the next y. Okay, so the next y is going to be this current y, which is 1, plus the delta y, which is going to be the derivative times the delta x. So we know the delta x is 0.1. I'm going to put that in here. To get this derivative, we're going to take the equation that gives the derivative, and I'm going to plug this current location in for x and y. So this is going to be, for that derivative, 0.2 times x is 1 times y is 1, and then multiplied by delta x, which is 0.1. And if you do that in a calculator, you end up getting that this is 1.02. So that means that when I move up to 1.1, so if I go a delta x of 0.1, the delta y takes me up to 1.02. Okay, so just kind of graphically what we did was we said we're starting at 1, 1. We moved 0.1 away, and we went up to 1.02. So we went from 1.11 to the point 1.1, 1.02. And that's another point that's on the solution curve. So I'm tracing out a little piece of the solution curve. Right? Then I'm going to do another iteration. So the same procedure, but now I'm using 1.1 for x and 1.02 for y. So the next y is going to be the current y of 1.02 plus the derivative, which is this up here, 0.2 times the x, which is 1.1 over here, times the y, which is 1.02, and then all of that times the delta x, which is 0.1, and that gives me 1.04244. Right, so when I move up to 1.2, I'm at a y of 1.04244. And you want to try to keep all of the decimal places here because little tiny errors can add, get bigger and bigger as you keep using the results of everything. Okay, the next step, same thing. Y equals the current y of 1.04244 plus the derivative, which is 0.2 times x times y. And then that derivative times the delta x. When we multiply this out, you get 1.0674 and a bunch of other numbers. I'm just going to put dot, dot, dot. But in your calculator, you can just keep adding this on. I'm not sure if I should show that or not. Maybe I should show that, just so you can see mechanically what this looks like. Yeah, since there's only one more example, I will show that on this example. So if I was doing this, what I would do is just start with this calculation. So I have 1 plus 0.2 times 1 times 1 times 0.1, and then I have this answer on the screen, 1.02, and I copy it down here. Right, then we're starting at that same location, so I just take that as is, and then add 0.2 times 1.1 times 1.02 times 0.1, and then that gives me the 1.04244 number. And then I would write it down here. To do the next one, I don't have to recopy it, it's already in my calculator. I'm just starting with that, and then add, and then put this expression in. 0.2 times 1.2 times 1.04244 times 0.1, and that gives me this 1.0674 number. Now it's getting pretty long, so usually at this point I would write like some of it out and put dot, 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 and then I would also do that here. I would say this is, now we're up to 1.3, and this is 1.0674 dot, 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 but when I write this, it's 1.0674 dot, 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 plus 0.2 times 1.3 times 1.0674 dot 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 times 0.1. I'm still going to use the unrounded version in my calculator. So when I do the next step here, I'm going to say that plus, and then 0.2 times 1.3 times. Now I need to have this number, but I can just say plus or multiply and go up here and grab the unrounded number and then multiply that by 0.1 and then write the next result. So I'm continuing to use the unrounded version in the calculations. I'm just writing down an abbreviation of the version of this, but we can still use the unrounded version. So this would turn out to be 1.0952 with more detail. And that means we would be at 1.4, 1.0952 and some stuff. So then the next y would be that same 1.0952 plus the derivative, which is 0.2 times x times y, 1.0952 something, times 0.1, and that gives me 1.125878 and some things, which means that now we would have 1.5, 1.125878, and more detail. Okay. Now what they asked us to do was to come up with a 4-decimal approximation for y at x is 1.5, and now we're here. So now I can say, therefore, y at 1.5 is approximately equal to, and then I'll take this number and I'll round it to 4 decimal places, 1.125. Okay, so that's it. That's Euler's method. It's very procedural. It's somewhat tedious, but it's good to know, and it does mean that we can dot by dot approximate the shape of the function curve as accurately as we want it. And the smaller the step size, the more accurate it's going to be, but then the more steps it takes to get a certain distance away from the initial x. Okay, one last example. Maybe try pausing the video and try this. This one's a little different. Instead of being given an equation for the derivative, we're actually given a table that has the derivative values pre-worked out at specific x locations. So try this problem using that table. Okay, to solve this, we're trying to approximate f of 2, starting at f of 1 with a step size of 1/2. So I would make the table here and say we've got x, y pairs. We're just figuring out f prime of x that comes from the table. And we're starting at x is 1, y is 4. So we're at 1, 4. So using Euler's method, the y will be equal to the current y, the next y will be equal to the current y plus the derivative. And so the derivative here at 1, 4 is x is 1. This table just tells me that that derivative is 0.2 times the step size, which is 1/2. So this one actually we can do with our calculator. And sometimes these do happen on the non-calculated part of the AP exam. So let's do that. This is the same as in fraction form, 0.2, but this is 1/2. Right, so that's 0.2 times 1/2, which is 4 times half of that, which is 0.1, which is 4.1. Right, so even without a calculator, is it 4? Yeah, it would be 4.1. Okay, then I'm going to write that we went up to 1.5, and now we have that this is 4.1 for the y. Right, then we'll do this over again. So now this is 4.1 plus the derivative at x is 1.5, and you tell me that is 0.5 in the table, times 0.5. So now I have 4.1 plus 1/2 times 1/2. So maybe I can write that this way. This half is 0.5 times 1/2. That's just going to be 0.25. So this is 4.1 plus 0.25, which is 4.35. Right? So even without a calculator, we can see that is 4.35. And at this point, we are at the target x of f2, so we can see therefore f of 2 is approximately equal to 4.350. All right, and there was no rounding anywhere in there. So it's still not the exact answer, right? Here's the curve, and we approximated with these tangent lines. So even though this didn't require any rounding, it's still an approximation because the tangent lines projected are not going to be at the same place as the curve. All right, and that's really it. Once you've done a couple of them, they're done the same way every time. So just very procedural.